Let's take a look at number 17. Number 17 reads, a force of 3 times 10 to the negative second newtons is needed to move a charge of 56 microcoulombs a distance of 11 centimeters in the direction of a uniform electric field. What is the potential difference that will provide this force? So the first thing we want to do is try to visualize what's going on. This was one of the electric field simulations that we had in our computer lab. And what's cool about this is you can try to visualize in 3D what this looks like here. So one way to picture an electric field is to think of it as a 3D space changing around a charged object. And in this case, we have a positively charged source here, and the positive test charge particles are flowing away from that positive source here. We got a charged line, like a wire, think of it that way, okay? But the point is, an electric potential is like the height on an electric hill, and it takes energy to move charges to the top of a hill, and that's the job of a battery, a power source, or we use things that are called capacitors to store charge. And as that charge flows down that hill, those charges can do work, like run the screen of your iPhone, or when you're surfing the internet, or you're talking on your cell phone, or you're charging up electric ink to stick to the screen of your Kindle or the latest e-reader, etc. So this is kind of a picture of what's going on to try to visualize this here. So in step one, let's make a little sketch of what's going on here. We have some kind of electric field, and it doesn't really specify what it looks like. It just says that it's uniform. So I'm going to use this gravity analogy and draw it flowing down. Okay, here's my electric field. And then we're going to try to move some charge through this field. Let's think of it that way here. Okay. In step two, let's break down all the information that's given. So this was the information that was given. The force needed to move this charge was 3 times 10 to the negative second newtons. Next, the amount of charge was 56 microcoulombs. The Greek letter mu, micro, means a millionth. So that's 56 times 10 to the negative 6 coulombs. Usually when we're talking about microelectronics and computers, we're talking about really small amounts of charges, millionths of a coulomb. And then the distance the charge moves is 11 centimeters, which is just 0.11 meters. The final thing I want to point out is it's moving in the direction of a uniform electric field. So if you're moving in the same direction of the field, you're going down that hill. So the potential difference will end up being a negative voltage because we're going down. Okay? So anyways, let's take a look in our toolbox here. So the first thing is we want to be able to find the voltage based on the distance moving through a uniform field. So voltage is potential energy per charge. For a point charge, it's kQ over R, but in a uniform field, the change in voltage is the electric field times the distance you move. V equals E times D. So we're going to end up using V equals E times D. We have D, and it's going with the field, so it's a drop in voltage. So I guess technically we can go ahead and make this a negative number there. So we'll get a negative for a voltage drop, but we need to know E. So how can we find E? Let's look in our toolbox. E is simply equal to force per charge, F over Q. So we can find the strength of the electric field by looking at the amount of force needed to move our charge here. So now we can go ahead and plug and chug here in step 4 here. Okay, so first we'll find the strength of the electric field. E will be equal to the force, 3 times 10 to the negative second newtons, over the amount of charge that was present, which is 56 microcoulombs, 10 to the negative 6 coulombs. So let's get out our calculators, and we'll go ahead and plug and chug here. So if I put in 3 times 10 to the negative second, divide that by 56 microcoulombs, that's 10 to the negative 6, I get 5.36 times 10 to the second. Let's keep a couple decimal places, 5.357. Newtons per coulomb is the strength of my field. And now I can put that into my voltage equation. V is just equal to E multiplied by the distance of negative 0.11 meters. So all I'm going to do is, to find the final voltage, just multiply what I just got by 11 centimeters. And I get a final answer of negative 5.89 times 10 to the first, which is just, 58 volts is a way to think of it, okay? Negative, we can do scientific notation, that's fine. 5.89 times 10 to the first. And the units are volts. And there you go, that's number 17 in a nutshell. Kind of abstract, but trying to visualize how charges can move through a field, experience forces, and also energy, and in this case, a change in its potential, energy per charge. So, number 7. Actually, my bad. It's negative 5.89 times 10 to the first, not negative first, okay? Or negative 58.9 volts, another way to think of it.